Okay, so good evening, students. This is Dr. Dong. Today we're going to learn the uh, a new data structure named binary search tree. So, like before we talk about the new stuff, let's first review what we have learned from last week. So last week we mainly learned three new data structures, and they're stack, queue, and linked list. So if you remember, both stack and queue are still based on array. Okay, so they're still based on array, but they're different from array because we don't have to use up all the available spaces in the array. Instead, we can just use a small portion of that. So, but the difference between stack and queue is that stack implements a last in first out policy. You can always think of stack as the shelf in your supermarket. So the last item that comes to the shelf will be picked up by the customer first. And queue implements a first in first out policy. So you can take queue as a waiting list in the doctor's waiting room. Okay, and then we learn another data structure, so which is not based on array, and so its name is linked list. We said that linked list is like a list of nodes, and each node has three pieces of information, which includes the key, which is like what kind of value is stored in this node, plus a field named previous and a name named of next. Previous stores the link to the node before it, while next stores the link to the node after the current node. Okay, so with this kind of like the links, we even though for linked list we only keep track of the head, still only from the head we are able to go through all the nodes in the linked list. So, and also, if you remember, we said that the main purpose for us to propose this, for not for us, for those designers to propose these three data structures is because they provide very efficient operations for us to do insert and delete. Okay, so for all these three functions, they provide O1 complexity in the insertion and deletion operations. This is like no matter how many elements are there in the stack or queue or linked list, then that we will only need a constant amount of time for to insert or delete an element. And compared with array, so compared with the array, which only gives us O(n) complexity, this is a big improvement, and this is the main reason why we learn these three data structures. So you should use them in case that you need to do a lot of insertion and deletions over the array, because it can really help you to boost the efficiency of your program. So, but if you remember, okay, in linked list we learn a function named search. So in the search function, we said that we start from the head and we just compare the current node's key with the value that we want to search for. If it's a match, we just return this node. Otherwise, we just move to the next one until we visit all the nodes in the linked list. If we don't find anything, we will just return nil or null in Java to represent that the value does not exist in the linked list. And in the worst case, if there are unknowns in the linked list, we have to go through all of them in order to find the one that we are looking for. And the complexity is O(n) for linked list. Actually, for array, it's the same thing. Okay, or the search complexity of array is also O(n). It's like if you are giving an array whose size is n, we just inspect the elements from the first one until the last one to see if we can find the target that we want to search for. And also in the worst case, we have to go through all the possible places in the array, and so which gives us the O(n) complexity in search. So, but O(n) complexity is not very good, so if we need to do a lot of search operations in the data, then we probably will need to seek for help from a better data structure that is search. So, and this is the purpose why we learned the new data structure, whose name is binary search tree. And actually, here, as you can see that even the name of the data structure includes the word search, and this is the this is the reason why people design binary search tree, because it is very good at search. And so let's, without further ado, let's learn something about this data structure. So before introducing binary search tree, I would like to talk about one concept named tree. Okay, in computer science, we can define tree. So for example, so on the top we have the top node, and which has a couple of children nodes. Okay, and also like some children nodes also have more children nodes. Okay, so you can take it as this way. Okay, the top node is your grandparent. Okay, and then so your grandparent gives birth to a couple of to 3 kids, and one of them is your parents. Maybe just this one is your parents, and your parents give birth to you and the other people. Okay, so your siblings, and this is your aunt and your uncle, and these are your nephews or cousins. Sorry, these are your cousins. So so the tree structure is pretty much like the family tree, or the family ancestor structure in our real day life. So let's say if we have a pair of nodes, let's say node A and node B, and if there is a link from A to B, then we will say that A is the parent node, while B is the child node. Okay, and also like say if we trace your family all the way back to the oldest time, then actually for all the human beings there is only one common ancestor. So that is the first couple that we know on the earth. So they don't have any parent, because they are the first one that are come to our earth, so come to this planet. So for that couple, we give it a name, the name root. Okay, so a tree structure only has one root, so which is the top node, the node at the top level. There is only one single node, so it does not have any parent. Also, we call the nodes that do not have any child, like this one. They don't have any child. We call them leaf nodes. Okay, so for any node that does not have a child, we call them leaf node. Like most of you who do not have child, then we can call you the leaf node in a family ancestor tree. Okay, so this is the tree structure, and there is a special type of tree. We can call them binary tree. Okay, so you can take it this way. Okay, so so if we talk about a car again, I want to use the example of cars. Okay, so if we take tree as car, okay, as vehicle, then binary tree is pretty much like a two-door car. So we have a car that only comes with a 2 doors. So this is a special type of car. So binary tree is pretty much like a special type of binary tree is a special type of tree. And in order for a tree to become to be a binary tree, it has to satisfy a requirement, that is every node in the tree can only have at most two children nodes. Okay, so if for all the nodes in a tree structure, if each of them can only have at most two children nodes, then we say we call it a binary tree. So look at here, is this a tree or not? Obviously, it's not, because here for the root node, it already has 3 children nodes, which violates this requirement. So this is not a binary tree. But what about this one? Yes, this is a binary tree. Okay, this is a binary tree. The parent node only has two children node, and then this node has 2 children node. This node does not even have child. This node does not even have child. This node has 1 child, which is 8. This node does not have any child. Okay, here we say from here you can say the limitation of binary tree. So which is that every node in the tree can have at most 2 children nodes. And then let's look at another concept. Okay, so which is like binary search tree. Binary search tree. So you can take binary search tree as like a two-door convertible, so which has more limitation now. In order for, let's say in real life, in order for a two-door car to be a two-door convertible, it must have a roof which can be open and which we can open and close. Over here, for binary tree to be a binary search tree, it has to satisfy one more say requirement. That is, okay. So if for every such structure like parent node, left child node, and a right child node. Okay, so let's give them a name. X means the parent node, and L means it's left child, and R means it's right child. So it has to satisfy this relationship. Okay, so the value stored at X must be larger than or equal to the value stored at the left node, while less than or equal to the value stored at its right child. Okay, so if every such parent and child relationship satisfies this requirement, then we will call the binary tree a binary search tree. So for example, over here, let's check if this condition is satisfied or not. Okay, so first let's look at the root node. It is larger than its left child, while smaller than its right child. So it satisfies this requirement. Okay, it satisfies this requirement. And then let's look at another one. Okay, so for this node, it's larger than its left child and equal to its right child. Okay, still it satisfies the previous requirement. And also, let's look at this node. Okay, it does not have a left child, so we only need to check its right child. Okay, it is less than its right child. Okay, it also satisfies the requirement. So this tree is actually a binary search tree. Okay, and this is the definition of a binary search tree. And this requirement, we call it, for this requirement, we give it a name called binary search tree property. Binary search tree property. I want everybody to understand this property and also memorize that, because this is easy to memorize. As long as you remember this diagram, it's super easy for you to remember it. And more importantly, if you go to a coding interview for software engineer, okay, so there are usually 7 rounds, so 6 to 7 rounds of coding interviews, and each one is like they give you a question and ask you to implement that in the language that you prefer. So one of them, among these interview questions, one of them has to be the topic that we talk about, which is binary search tree. Okay, so when you go to your coding interview, and when you realize that you're handling a problem where you have to do a lot of search instead of a big bunch of numbers, you should always think about binary search tree. And that's the reason why I want everybody to be familiar with this property, because you are going to use that in your job interviews. Also, another concept that I have to talk about is the height of the tree. Let's say here, let's just count how many levels in the tree do we have. This is level 1, the first level, level 2, and level 3. So you can take it as like, let's count how many generations of people does a big family have. So we basically count them, and then the height is basically the number of levels in the tree. So for this example, we have 3 levels. So the height of the tree is just 3. Okay, and also here for each node in a tree, so previously when we linked the list, we define list node as this. So list node has 3. Every list node has 3 pieces of information, which are the key, kind of like denote the value stored in the node, and also it has the link to the node before it, which is the variables, and the member variable name is previous, and also it has list node next, which is the link to the node following the current node. Okay, so for binary search tree, we also have the similarly we also have the definition of tree node, because as you can see over here, a binary search tree basically consists of multiple nodes, and so for each node we define them in a structure in a class of tree node. Okay, so tree node has 4 pieces of information, which are this. Okay, integer key, which is like the value stored in this node, and besides it has 3 links. The first, so all of them have the type tree node, so which are P. We call it which is the parent node. Okay, so the node should know who is its parent, and also it has we just call them left and right. Tree node left and right. Okay, so which are the link to its left and or right child. So or sometimes we just use L and R, for the sake of simplicity. So okay, and if any of its parent or left or right child is empty, does not exist, we will use nil to represent that. So if we find for a node, if we find that its parent is nil, we know that it does not have a parent. So so this is the definition of the structure, and this is the property that I talk about. I call the binary search tree property. Okay, so for binary search tree, we're going to learn the following 7 operations, which are the traverse function. The traverse means that we are going to visit all the nodes in a tree, and we can visit the tree, all the nodes in a tree in different orders, which includes in order, pre-order, and post order. We're going to learn all of them, and then most importantly, we're going to learn the search function. So how do we perform search in a binary search tree? And also we're going to learn the function to find the minimum and maximum value inside a binary search tree. Also we're going to learn the successor function and the insertion function. Okay, so the deletion function, okay, we're not going to talk about that because it's super complicated for us to delete a node from a binary search tree. It's very complicated, so I'm going to skip that. And and also in your homework 5, you're going to implement the first 6 functions. This does not so you don't have to learn the delete function. Okay, so here let's say let's learn the first function, namely traverse. Okay, so traverse means that giving a binary search tree, we want to visit all the nodes inside the binary search tree. Okay, so so how do we do that? Let's look at this structure. Okay, so here we have, let's just look at a very simple structure where we have this. We have X as the parent node, and L as its left child, and R as its right child. Okay, So in order for us, so let's just focus on this simple structure. Okay, if we give if we want to traverse all the nodes over here, so first of all we are sitting at the parent node, so we are sitting at X. Okay, and we basically want to visit all the three nodes. And so there are three different options for us to do that. So the first or three orders for us to visit them. The first one we can call it pre-order. Okay, pre-order means that we are going to visit the parent prior to visiting its children nodes. So the order of traversal would be X, L, and R. So it's like we first visit the parent node, and then we visit its children nodes L and R. So and also there is another order named in order tree work. Okay, so in order is like we are going to visit the parent in between its children nodes. So the order would be left X and R. So we visit the parent node. So in between the left visiting the left and the right child. So the last one is called post order. So post order means that we are going to visit the parent after its children node. So the order would be L, R, and X. So we visit its two children nodes at first, and after that we visit the parent node. Okay, so this is the three different options. Let's first look at this option, this order called in order tree work. So in order tree work takes a single parameter named X. X is a tree node. Okay, X is the type of X is basically a tree node. So let's look at what it does. Okay, if X is not nil, meaning that we're not at a node that so X does exist. Okay, if X does exist, what it does is, like, remember here we're talking about in order. So with in order we need to visit its left child first, and then X, and then right child. Okay, so here the pseudocode is that we're going to call the same function to over its left child to make sure that we visit its left child first, and then we're going to print out the key stored at the node X. This is equivalent to here, say visit X, the parent node, and then we're going to visit its right child by calling the same function over its right child. Okay, so purely simple, right? Very, very simple. This is the function, and one thing that you need to note is that this function is calling itself. So this is called recursive function. Okay, this is a recursive function, and let's look at let's take an example and say so what if we apply the previous in order tree traverse algorithm? I'm going to write down the pseudocode over here. In order tree work X. So the pseudocode is like this is line 1, 2, 3, and 4. In line 1 we check if X is not nil. We are going to visit we are going to call the function. I'm going to use ITW, the first letter of these words to represent the function x.left, and then we're going to print x.key, and at last we're going to ITW is right child. Okay, so this is the pseudocode, same as what we learned before. Okay, so here let's look at, so here we're giving a tree, we are giving an instance of the binary search tree structure, and so also we have, let's look at the structure. Here we have 1, 2, 3, 4, 5 children nodes. So here we got 5 children nodes, and for each children node, so they do have, for each children node, it does have a left child and left and a right child, but their left and child are just nil. Okay, their left and the right child are just nil. So yes, it's like they have child, but they are, so it's like for a person, for a very young person, even though they don't have child, but they have the potential to have child. So okay, so so I'm just going to write down nil for this, the first two leaf nodes. Uh, to save some time, I'm not going to say continue writing it. Okay, so first we call the in order tree work function over the root node, which is right over here. So we are going to start start the in order tree work from the root node. So first let's check this function. Let's check the first line. When we are executing, this is the first time that we are calling this function, and then let's call it x1. So this is I'm using x1 to denote, okay, this is the first node we are going to pass into the in order tree work function. And so first we run the first line. If x is not empty, then we are going to call the same function over its left child. So I'm just going to make a note 2, meaning that we are executing its the second line of this function right at this instance call. Okay, instance call. So here we're going to invoke the same function again, but invoke the same function again, but the input parameter is going to be is the left child of root over here. Okay, so this is x2, and then so we're going to restart this function, but the difference is that, okay, so now we pass in x2, this node, the left child of the root node. So obviously this node is not empty, so we'll be able to pass the first line and go to the second line. In the second line, we're also going to invoke the same function over its left child. So here we just move to its left child, and so which stores the value 3. Okay, so again we're going to start a new function, but the input parameter is just this node. Okay, so we first check if it's empty or not. No, it's not nil, so we're going to execute the second line and invoke another function called at its left child. So this is the fourth time we invoke this function. And then, so first we check if it's empty or not. It's not. So then we're going to, so we are going to go to the execute the second line, and so which calls the function over its left child. Okay, so this is the fifth time that we're going to call the function, but here we're calling the function over a node that is nil. So over this function call, this condition, if x is not nil, will be a false. So we will not do anything over here. So we just do nothing and finish the function call at 5. So at this node. Okay, so then we go back to the previous function call over the node 2, and so we just finish executing the second line in that function call. So we are going to go to execute the third line, which is to print out the key at this node. So the first value that we're going to print out is 2. Okay, so because this node stores the value 2, and then so we are going to invoke the last line of the function, and so execute the last line of the function, and then we are going to invoke the same function call over its right child. So this is the sixth time we call the function. Again, we are calling it to add a new node, so it's going to fail the first check. So we will not do anything over there, and then we just finish the function call at this node. Okay, so remember we trigger the function call at this node from x3. Okay, so at x3 we just finished the second line, so we're going to go to the third line where in which we're going to print out the key stored at x3, and the value is actually 3. So the second number that we print out is 3. And then so we're going to we're going to visit so we just finished the third line, and then we're going to execute the fourth line in that function call, in which we call this the in order tree work function over its right child. So we just go right over here, and this is the seventh time we call this function. So very similar to to its sibling over the node that stores 2. Okay, so we're so like when we are at this node, what we did is actually what we see in the output is like we just print out the key stored at the node and then do nothing. So this is going to be what we do over here. So we just print out the key stored at this node, which is 4. So the third value that we see in the output is 4. And then so we finish the function call at this node, and then we'll be able to go back to the function call at the node 3, and so in which we just finish the function call, because we just finished the last line, the fourth line. So we finish over here. So it's like we finish visiting this part of the boundary search tree, and then so we're going back to the function call at 2. Okay, at x2, and so in which we just finished the second line. So we're going to go to the execute the third line, in which we print out the key store at this node, which is 6. Okay, and then we're going to execute the fourth line in that function call by invoking the function at its right child. So this is the 8th time that we call the function. So and so this is in the fourth line we invoke that function. Okay, right at this node. So first, this node is not empty, so we're going to execute. The second line actually its left child is empty, so we're not going to do anything over there. And then when we finish the second line, we're just going to execute the third line by print out the key at this node, so which is 7. Okay, so and then we are going to execute the fourth line, okay, by triggering the function call over its right child. So we take it as x9, and at x9 we first check if this node is empty or not. It's not, so we're going to call its second line, and by invoking a function call at its left child. So this is, we take it as x10. At x10, what we do is that we just print out the value stored at this node, and then we see an output 9, and then we just finish the function call right over here. So we will go back to x we just finished the function call at x10, so we will go back to x9. At x9 we just finished the second line, so we are going to execute the third line, in which we print the key. So we are going to see 13 being printed out, and then we're going to invoke the function to execute the last line, in which is like we invoke a function call at this node, which is empty. So we don't do anything, and then we just finish the function call at this node. Similarly, we just finish the function call at this node. So this is like we finish this part, and then for x2 we just finish its last line. So we just close that function call. So it's like we finish visiting this part of the binary search tree, and then so we are going to the line 2. So we just finished line 2 at the function call over x1, which is the root node. So we're going to execute line 3 by print out and print out the value stored at the root node. So we're going to see 15 being printed out, and then we're going to execute line 4, which goes to its right child. Okay, so this is x11, and at this node, what we do is that we're going to, so similar to right over here, we're just going to visit its left child first, and then so print out the value at its left child, and then this parent node and its right child. So which is like, so the output that we're going to see is this 17, 18 and 20. Okay, so then we close this function, so we finish the function call. So in total, the in order tree traverse function will print out the values in the tree like this. Okay, so here I'm just going to ask you, do you see anything that is interesting? Yes. So the interesting thing is that we basically print out all the values from the lowest to the largest in order, in the correct order, in the ascending order. Okay, so yes, is this by accident or is this for sure? Think about it. So actually it is for sure, and because why? Remember, so in order is going to visit the left child first, then parent node, and then right child. So the binary search tree the binary search tree property states that x is larger than or equal to its left child, and larger than or equal to its left child, but smaller than or equal to its right child. Okay, so right over here we have this relationship, and so as to this. Okay, so that's why we are going to see the values being printed out in ascending order. That's for sure, but only in order we'll do that, because for pre-order we don't have that ascending order. Okay, and similarly for post order we don't have that. Okay, so this is the why I'm just going to focus on the in-order tree traverse. And actually, so if you understand in-order tree work, it's super easy for you to change it to pre-order. If you want to change it to pre-order, it's like the only difference between in-order and pre-order is at the order when we visit the parent node and the left child. So actually, if you switch these two lines, it will be we visit x first and then it's x. So this will be pre-order. Okay, this will be pre-order. And if you switch the position of these two lines, then we got left and right and x. So this will be post order. So this is if you switch these two lines, it will be post order. So it's when you are doing your homework 5, it's super easy for after you finish implementing your in order tree work function. It's super easy for you to change it to be pre-order and post order. And actually, this is one question that I received. I got a lot of emails. So regarding homework 4, in homework 4, you are asked to implement the linked list, stack, and queue. And some of the students actually finish homework 4 pretty early, like 5 days before the due date. And they do send me, some of them do send me an email asking me if the output that they see from their code is correct or not. Yes, I think some of you are wondering that after you spend like many hours just debugging your code and finally you see something printed out, correct? As you desperately want to know if that is correct or not. I absolutely understand it, but I'm not going to provide the correct output for each and every homework. I'm not going to do that for any homework. And the reason is pretty simple. Okay, if you have a very good understanding of the structure, like for example for stack, you know what does the the push and pop function does, and then if you just look at the main function of stack.java, it's super easy for you to figure out what is the correct output, what kind of output are if you implement. So it's super easy. Okay, if you understand the push and pop function just by looking at the main function, you should be able to tell what kind of output are you do you expect to see. Okay, should you see. And in that way, okay, you will be able to so after you finish implementing your code, you'll be able to check if your code is correct or not. So here as I said, I'm not going to provide the correct output for the homework because I ask you I ask you to have a good understanding of the algorithm. Okay, so not so you can you shouldn't only earn credit from implementing something, but you should also so your credit also includes the understanding of it. So that's the reason why I'm not going to do so. If you have a good understanding of the algorithm, you should be able to tell what is the correct output, and then by just checking it with your implementation, yes, you know if you can submit your homework or not, right? So I'm going to keep this routine for all the remaining homeworks. Okay, and also another question that I received from the students is that when can you see the grade of your homeworks? So far we have three homeworks which have already passed the due date. And actually in this course I am not going to grade the assignments. It is the TA or GA. So for this course, the department does give us a GA to help with all the gradings. So I have already sent the grading rubrics to him. So he will start. He told me that he will start grading this week. I would say that for so at least my expectation is that by the end of next week he should finish grading the first three homeworks. Okay, so don't worry about that. And actually, I'm pretty generous at the grading rubrics. As long as you show your efforts, even though your code, the output from your code is not correct, as long as you show your efforts, you'll be able to get partial credit. Hope that this is fine with you. Okay, so the last thing that I want to talk about the tree work function is what is the complexity. So here we're talking about complexity in terms of n, where n denotes the number of nodes in a tree, and actually here the complexity is O(n) because we're going to visit each node exactly once. So that's why we have the O(n) complexity, and the next function that we're going to inspect is search. So here I'm going to remove all my nodes. The previous nodes. Okay, so here I'm just I'm going to ask you one question. Okay, so here if I ask you to search for the value 13 from the tree, and you only know the root of the tree. Okay, you only start from the root of the tree. So like you are standing at the root of the tree, and I'll ask you to search for the value 13. So starting from the root, so you know that okay, the root does not have the value that you want to search for, so definitely you need to go down. So basically here you have two ways. You can go left and then you can go right. So which direction are you going to pick? So some of you may say, okay, I want to go both directions because I don't want to miss anything. But let me ask you another question. Okay, here if we want to search for the value 13, is there any meaning if we go right? If we just turn right, is there any meaning? So the answer is there is no meaning, because if we look at this part, all the values are larger than or equal to the root value. And since the root value is already larger than the key that we want to search for, so this part is going to be of no meaning for us. So we can totally ignore that. So from the root node, you only need to go left. So even though we have two directions, you only need to go left, turn left. And then here you reach the node 6, the node that includes the value 6. And so which way are you going to go? Yes, you are going to go right, because all the values to the left of the node 6 is going to be less than or equal to 6. So which is definitely not of interest to you. So you basically go right, and then at the node 7, you know that you are going to turn right because 13 is larger than 7. Go over here, and then you reach the node that includes the value that you want to search for. So this is the process of search. Okay, so here let's say how many nodes did we visit in the search process. Okay, so here let me use a different color. I'm going to use the red color to denote the nodes that we have visited. Okay, so here we visited 1, 2, 3, 4 nodes. Okay, on level, let's make it slow. Okay, on level 1, how many nodes have we visited? 1. On level 2, how many nodes have we visited? 1. On level 3, how many nodes did we visit? 1. On level 4, how many nodes did we visit? 1. So it's like on each level in the search process, no matter how many nodes are there on each level, we are going to visit at most 1 node per level. Okay, so for each level we are going to visit at most 1 node. It's possible that we for some levels we can ignore them because we just terminated the search process early. For example, right over here, we don't need to visit any node on the last level. So okay, so for each level it's going to be either 1 or 0. Okay, so if I tell you that we have h levels, the height of the tree is h, meaning that we have h levels in a tree, then how many nodes are we going to visit at most? In total, we are going to visit at most h nodes, because on each level we are going to visit at most 1 node. So the sum of h levels is just going to be less than or equal to h. So then the search complexity of the search complexity in binary search tree is going to be OH. Okay, so h is the height of the tree, and this is the first time that we use a different character other than n to denote the complexity. So some of you may wonder, okay, what is the relationship between h and n, where h is the height and n is the number of nodes in the binary search tree? So, and I'm going to just give you the conclusion. I'm not going to show the process to infer that because it's too mathematical. Okay, so here what we can say is that h is larger than or equal to log n, but less than or equal to n. Yes, so h is in between log n and n. So okay, so this is what we know, and here you can see that OH is definitely less than or equal to ON, and actually on average it will give us h is around log n. So here we can see that O log n is definitely less than ON. So here, this is the main reason why we propose when we learn binary search tree, because the search complexity of it is going to be significantly lower than searching in a linked list or an array. Okay, so here let's go back to the pseudocode. So after we know the previous procedure, it's going to be relatively easy to understand the search procedure. So here in a search function, we have 2 parameters. X is a tree node, and k is an integer that we want to search for. Okay, tree node. So first, if x is nil or k equal to key. So let's look at this condition. If k is equal to the key stored at x, it means that x stores the value that we want to search for. So we will just return the node that includes the value that we want to search for. But what about x equal to nil? What about x equal to nil? Why, when x is nil, we should return? This is because, for example, at here, if we don't want to search for the value, for example, if we don't want to search for the value 13, we just want to search for the value 14. Let's look at the what is the procedure. It's going to be relatively similar, but there is some difference. Okay, so here we're going to start again. We start from the root node. We turn left because 14 is less than 15, and then we're going to make a right turn over here because 14 is larger than 6. 14 is larger than 7, so we're going to make a right turn. And then at 13 we're going to make a right turn. And here we are going to move to this node, the right child of 13, which is neo. Okay, so the last step of the search process is here. Okay, x is at the node, is at a neo node, meaning that okay, so if x is neo, it means that you are searching out of the bound, out of the range of the tree. We are searching one level below the tree. So it means that the value that we want to search for does not exist in the tree. So that's why if x is neo, we also return x. If we return neo, it means that the value that we want to search for does not exist in a tree. Okay, so otherwise, if the value that we want to search for is less than the key stored at x, we just turn left. So we just call the tree search function over the left child of x. Otherwise, we just turn right. So fairly simple, right? So this is the tree search function, okay, this is the tree search function. And next, I'm going to talk about the minimum function. So here, for example, if I present such a tree to you, okay, such a binary search tree to you. So if I ask you, so what is the minimum value inside the binary search tree? So most of you would say, okay, it is 2 right over here. And then, but if I ask a different question, okay, say, what is the largest value in the binary search tree? And so after a closer looker, some of you may say, okay, it is right over here. Some of you may say it's right over here, which at the rightmost node, which has the value 20. Okay, yes, true. So yes, in a binary search tree, the smallest value is going to be stored at the leftmost node. So this is because, so if we go left, we are just going to go to a smaller value. Okay, so it's like if we go to the leftmost node, if there is no more left, it means that the value is the smallest. Similarly, if we go to the rightmost node, the value is going to be the largest. So these are the functions that help us to find the minimum and the node that includes the minimum value and maximum value inside a binary search tree. So this is the function that helps us to find the minimum value. Again, x is a tree node. X is a tree node. So while x is dot left is not neo, meaning that if x has a left child, we move x to its left child. So it's like we go one. So it's like if there is one place in the left, if we can go left, we go left until there is no more left, and then finally we just return the node. So similarly, the function to find the maximum value is just like we just replace left with right, and then that's it. Okay, so again, the function to find the minimum and maximum value inside a binary search tree is also OH, because for each level we're just going to visit either the leftmost node or the rightmost node. So in total we're going to visit at most H nodes. So here the complexity is also OH. And now we're going to learn a function that is a little bit more complicated. So its name is called successor. So before I introduce the function, I just want to define the successor of a node. Here, if I say that we want to search for the successor of the node 13, it means that we want to search for a node x which stores the smallest value that is larger than 13. Okay, here we're looking for the smallest value. If this is x, if this is x, then we basically want to find y such the successor of x is y such that y stores the smallest so the value stored at x, so the y dot key is just larger than or equal to x dot key, so meaning that the key at x at y is the smallest key that is larger than the key at x. So here the smallest value that is larger than 13 is 15. Okay, so the root node is the successor of x. Okay, so let me just take another example. So here, if I ask you, let me say, what is the, if we take this node as x, the root node as x, what is the smallest value that is larger than 15? It is right over here. It's 17. Okay, so this node is the successor of the root node. Okay, so this is the concept of successors. So it's the node that stores the smallest value that is larger than the values. Okay, so so here let's look at this. Suppose here we want to search for let's look at this node. Okay, so if we take this node as x, which stores the value 7, we want to search for its successor. So here this node has a right child. Okay, it has a right child if we go down in the hierarchy of the tree. So definitely we need to go to let me make it easier. Okay, so let me make it easier. So here let's target on a different node. Let's look at this node. It stores the value 6 if we want to find its successor. Here this node has both left and right child. Okay, so if we want to find its successor, we don't even need to go to its left child, because all the values stored to its left are less than it. So we just need to go right. Okay, so if we want to go right, we just need to find the minimum value to its right, so which is this node. Sorry, which is just this node. Okay, so this is y. Okay, so it's fairly simple. If x dot right is not null, if the x has a right child, then we go to find the minimum value right below its right child. Okay, so this is the logic. However, let's look at a different case. Okay, here if we take 13, the node stores the value 13 as x. Unfortunately, it does not have a right child. So what do we do? So it means that we cannot go down, because if we don't have a down right to go, but we cannot go down left, because it's not going to help us. So we can only go up. So first we go one level up to find its successor. So we make a left turn. When we go up, if we make a left turn, it means that we find a value that is more, so it satisfies this relationship. Okay, so the value that we encounter at that node is going to be smaller than 13, and then we go another left, we go another top, we go another up. Again, it's upper left. So this is not going to help us, and then we move another level up. So this is we go upper right. So this is the first time we go upper right, and then we just stop. It's guaranteed that this node is the successor of x. So this is the successor. Okay, so so here to summarize, if x does not have a right child, we just keep going up until we make the first upper right. So this is the logic, and then let's look at the pseudocode. Okay, so let's look at the pseudocode. Here we take this node as x, and So it's going to, so we don't need to we just skip the first two lines and go to the third line. Y is x dot p. So y is the parent of x. So the parent of x is just right over here. We have y as here. Let me use a different color. This is x and this is y. And then while y is not nil and x equal to y dot right. So here this is true. Y is not nil. X is y dot right. So this is also true. True and true is true. So we can execute the next two statements. X equal to y. X equal to y. So basically we are assigning y to x. So we move x one level up to y, and also we have y equal to y dot p. So y dot p is here. So we move y, also we move y one level up. So we move y to here. So we just move both x and y one level up. And again, y is the parent of x. So here, let's go back to the while condition to see if it's correct. It's true or false. Y is not nil. Y is right over here. It's not nil. And x equal to y dot right is also true. So we can execute the next two statements. We have x equal to y. So again, we move x one level up. We move x here, and then we are going to. So next we have y equal to y dot p. Y dot p is the root node. So we are basically moving y one level up to the root node. Okay. So here we are moving both x and y one level up, and here we have while y is not nil. So this is true. This is true. X equal to y dot right, and here this is false because x is the left child of y. So we are just going to stop and then stop the while loop and then return y. So this is the successor of the node that stores the value 13. So the reason why when we only stop when we x equal to y dot right, if x is y dot right, meaning that when we go up right. So at that time, it's guaranteed that we find the successor of x. So this is the procedure of the successor function, and the time complexity is also OH. H is the height of the tree because at most we're going to move both x and y h levels up. So that's why we have the OH complexity. Okay, so this is the first part of binary search tree, and I know that some of you may already feel your head is exploded already, but still I'm going to continue, okay? Because we have one more function to learn, that is the insertion, and I promise that it won't take a long time. So actually, if you, at this time you feel that your head is going to explode, I will feel personally. I will feel, okay, this is my job. This is what I'm exposed to do, because this means that you're really learning, and this also means that my explanation makes you think and makes you so your hard work, and this means I'm doing a okay job. Maybe not good, but at least it's okay. So here after this week, after the binary search tree, then we just finished covering the first two sections of our course, which are the sorting algorithms and basic data structures. So in other words, we are almost a half of the semester. Okay, so we just spent a little bit over 1 month together. So I'm not sure how do you like the past month, past 6 weeks. I'm not sure how do you like it. So specifically, I'm not sure if you like my teaching or not. So do you think that I'm going too fast, or do you think that I'm too talkative? So I don't know. and but I do want your opinions. So I do need your feedback in order to better prepare my teaching for the rest of the semester. So definitely I'm not going to ask you to say send me an email saying what do you like and what you don't like with this course, because you do want your privacy, and I do respect your privacy. Um, if you send me an email saying that, professor, I think that you're a terrible professor, then you may be afraid that I'm going to give you a F grade. Actually, I'm not. So here in the United States, I think most of you are quite familiar with a website, which is the Yelp for professors, and that website is called this readmyprofessor.com. Professor.com. I'm not sure if you have visited this webpage or not. I think most of you should have. If you haven't heard about this webpage before, you should use this one, because for the future, before you register a course, you may find, okay, section 1 is taught by Professor A, section 2 is taught by Professor B, and section 3 is taught by Professor C. So here it's like you have a choice. For the same course, you have the choice of multiple professors, and you really want to know who is the best one. Okay, you don't want to waste your money and your time just going to going to the lectures taught by a professor that are not good at teaching or do not care about teaching. So like when I was a student, I did the same thing. Like just at the time of registration, I'm just going to search for go to that famous website and find the reviews on different professors. Okay, so here in the okay, if you go to that famous website, read my professor. Yes, read my professor, and over here, if you just search my name, and I know that my name is really unique, or it's not unique. It sounds very strange for you, and but so sometimes it is causing trouble for me, because people have difficulty memorizing me. But the good thing is that if you search for my name on the internet, there just only one person with this name in the United States, either on LinkedIn or on Google Scholar, etc., etc. Also, similar for with my professors. So here, if you go to that website and type in my name, you should be able to find me. So this is me. Okay, so I actually so go over this website maybe every at least every month to find what students like and why students like and do not like me. And so far, you can see that I got 40 ratings, and yes, most of them are pretty positive. I'm pretty proud that out of these 40 ratings, there are like 39 of them are just five star. Only one is like this one is like 4.0, and so here so if this semester is like usual, or it's like the previous semesters, when I can have face-to-face teaching with almost every students, and then I'm not going to worry too much, because I'm confident in my teaching, and I do care about the learning experience of my students. So that's why I got very positive ratings from that readmyprofessor.com. And actually, it's pretty funny. When I showed that website one day after, like maybe just 2 years after I started my job at Montclair, and one day, the first time I found, okay, someone reads me on that website. At that time, there were like 10 ratings, and all of them are 5. So 5 out of 5. So I was pretty proud. So I just showed it to my wife. My wife asked me, did you provide your students or filling out those responses by yourself? I said, how come? So yes, yeah, like even though I do I do so I spent quite some time on teaching. um, I can't expect that level of reading. But for this semester I'm not that confident because we are doing totally remote for most students. And um, also I'm just so if you do not choose to come to campus for the face-to-face class, then um, so most likely you're just watching my videos, and I'm not sure if you like it or not. What do you like and what you don't like? Even though yes, some students take the advantage of my office hours and ask questions during that time. So so um, so I do need your feedbacks. What do you like and what you don't like? Just be frank on that web page. I'm going to check the next week, and hopefully I can see some responses, new responses, and I'm going to accommodate my teaching material based on your suggestions. And yes, just give me your frank reading, or not reading. I don't care about that much. I just need your opinion or suggestions to improve my teaching. Okay, so next we're going to learn the insertion function for binary search tree. Okay, so for binary search tree we are going to learn the insertion function with this. Okay, the input is t, where t is a binary search tree. Okay, it's a binary search tree. For t we only binary search tree we only know the root node. Okay, the root node, and we got a z. Z is a new node. Okay, a new node. If you remember, z had a new node, a new tree node. So z has 4 fields: z dot key, z dot left, right, and parent. Okay, so this function helps us to insert the new node into the tree. Okay, so let's look at the example over here. Okay, suppose we got a new node which stores the value 13 as z, and we have tree. Okay, we have t, and we start from the root of the tree. So here with this, so let's just cross this node. Okay, let's just cross it. So let's say starting from the root, because we want to insert new node z which has value 13, so definitely we need to go right. And then we are at this node, then we know that we need to turn left. We're at this node, we know that we need to turn left. And since this node does not have a left child, we know that okay, we should place z, the new node, with the value 13 over here. And this is the insertion process. So it's pretty much like search, but with some additional work. So let's go through it, this pseudocode with this example. Okay, so again we have this t, we have this tree structure, we have this t as the tree, and we have z which stores the value 13. Okay, so first we have y equal to nil and x equal to t dot root. We have x equal to the t dot root, y is nil, and x is t dot root. So here I'm just going to ask a question from you. So if x is the root of the tree and y is nil, what kind of relationship can there be between x and y? Think about it. So yes. So y can be x's parent because the root node does not have any parent. So its parent for root node, its parent is just the nil. So yes, y can be x parent. So here y is x parent. So we are going to keep this relationship consistent. Okay, so next, while x is not nil, we are going to the third line. While x is not nil, so x is not nil, we have y equal to x. So we have y over here, and if z dot key is less than x dot key, we have z dot key as 13, x dot key as 12. So this is false. We are going to execute the else statement, else x equal to x dot right. So we're going to move x to its right. So we're going to move x to here, okay? So again here, y is the parent of x. Both of them go one level down. So, and then let's go back to the while loop. So here we have with x is not nil, this is true, then we're going to do this. Y equal to x, we're going to move y to this place, and we're going to check the relationship between z dot key and x dot key. Here z dot key remain the same while x dot key is 18, so this is true. We're going to execute x equal to x dot left, so we're going to move x to its left, so we have x right over here. Okay, so again we move both x and y one level down, and then we go back to check it. So while x is not nil, x is still not nil, so we're going to execute y equal to x. So we move y to here, and we assign x to y. So we move y one level down, and then we're comparing the key between z and x. So here we have x dot key as 15, so this is true. So we move x to its left. So now x comes to its left, which is nil. Okay, so we have x as nil. And so then when we go back to the while loop, we say, okay, this condition is false. So then we're going to terminate the for loop. So right up until here, we're just basically find the location to insert z, okay, to insert the new node z. So we should actually place z at the position of x. So next what it does is that, okay, it has z dot p equal to y. So it's like so it's like from z we know its parent is y, but y does not have any idea about whether it should take z as its left child or right child. So next we're going to do this. If y equal to if y is nil, then t dot root is z, so we can forget about that. And then if z dot key is less than y dot key, here we have z dot key as 13, y dot key as 15, so this is true. We're going to take z as the left child of y. So with this, it's like finally we are placing z right over here as the left child of y, and then we finish the insertion process. Okay, this is the insertion procedure, and the search complexity is the insertion complexity is also OH. H is the height of the tree. This is because we're going to move y and x from the top of the tree at most until the bottom of it. So at most we're going to move them H levels. Okay, so this is the insertion function, and some of you may wonder, okay, what about the deletion function? It's really complicated, and I assure you that even though you go to the Google's job interview, coding interview, they're not going to ask you to implement the deletion function of binary search tree, because they're not going to be able to remember it. And this is the procedure. Okay, so but this function, the design of this function is really interesting. So if you have time, you can go over it by yourself. Okay, so so this is the structure, the binary search tree structure. So we learned 6 functions: traverse, search, minimum, maximum, successor, insertion. Okay, and from all these 6 functions, 5 of them have OH complexity, where H is the height of the tree. Here you can see that the performance of binary search tree highly depends on the height. So we basically want the height to be as low as possible. Remember that h is in the range from log n to n, and so we want h to be as close to log n as possible. Here then people just to make sure that to make sure this happen, people just design a variation of tree structure named the red black tree, so which ensures that h is log n. Okay, which just ensures h is log n. So but that structure is way too more complicated. So I'm going to skip that. If you are interested, you can read chapter 13.2 and 13.3 to have a good understanding of that. Okay, so this is our material for week 6, and let me say, yes, week 5, actually week 5, and so have a proper week, and also remember that homework 5 is going to be published in the meanwhile. So